Yeah, in this video we will see Kahn's algorithm. In the last video we discussed about topological sorting, what is mean by a topological sorting and how to find out the topological sorting using depth first search. This video talks about BFS method of finding it, and BFS method of finding topological sorting is also called as Kahn's algorithm. And this is the sample graph I have taken, and the process of this algorithm or the steps involved in this algorithm are as here or as shown here. First one is we have to calculate the in degree of all nodes. Now first we will do that. If you see the in degree of this 0 node, nothing is there, right, as an in degree. Like there are no incoming edges. In degree is nothing but how many incoming edges are there for that node. Here there are no incoming edges, so the in degree becomes 0. And for 0, how many incoming edges are there? There are 2 incoming edges, so in degree of 0 is 2. And for 4, there is no incoming edge, so 0 is the in degree of 4. And for 1, how many incoming edges are there? 2. So 2 is the in degree of this. And for 3, how many incoming edges are there? There is only one incoming edge. 1 is the in degree of this. And for 2, there is only one incoming edge and 1 is the in degree of this. Now we are done with the first process. And the second process is, as I have already said, this is a BFS algorithm. Whenever we say that it is a BFS algorithm, the data structure used in breadth first search is queue, and in DFS we use stack, right? So we use a queue, and what are we doing? We will push 0 in degree nodes to the queue. Okay. Now what I'll do is, let's say I'll create a queue. Now first I'll push the 0 in degree nodes. 5, 4. 5, 4 are having 0 in degree. I can push it in any order. Either I can push 5 first and then 4 second, or I can push 4 first and 5 second. Anything, like any order I can follow. Now I have pushed it. 5, 4. Now why are we going with 0 in degree means, as we have said in the topological order, the nodes that comes first in the topological order are not dependent on any tasks. Those tasks should start first. So it means that there are no incoming edges. If you say that if you are starting a task and that is not dependent on any other task, it means that nothing is coming here, like no incoming edge is there. Now since in the topological order, first tasks are not dependent on any other tasks, right? So that's why here first we will take the 0 in degree nodes, because if you see 5, 4 here, 5, 4 and 4 are not dependent on any other tasks. We can independently start these tasks. That's why first we will take the 0 in degree. Now I have done that. Now the next step here is pop the node from the queue and reduce the in degree of its vertices. So what it means is, first I pop out 5. When I pop out 5, like basically when I remove this node from a graph, when I remove this node, these edges also will be removed, right? Because when I remove this node, whatever the edges that comes from this node are also removed. So when I remove these, the adjacent vertices, what are the adjacent vertices of 5? 1 and 2. Adjacent vertices in degree will be reduced by 1. Now here the in degree of 0 is 2, but here but since 5 is removed, it should get reduced by 1. So now in degree of 0 becomes 1, and in degree of 2 becomes 0, because this incoming edge is removed. So there are no incoming edges to 2. So the in degree of 2 had become 0 and in degree of 0 had become 1. Now when we are doing this process, while we are updating this, if any nodes in degree become 0, you have to push that to the queue. Okay. Now what I have done here, I have reduced in degree of 2 and 0, but 2's in degree is still 1, it hasn't become 0. but 2's in degree has reduced to 0. So I have pushed 0 to the Q, 2 to the Q. While popping out, here I have popped out 5, right? I should output, like to my output I have to add this vertex. Now I am done with this. I have pushed the adjacent vertices so as well. Now the second node is 4. Now you have to pop out and I'll add it to the result. While popping out, here if you see, pop the node from the Q and reduce the in degree of its vertices. After reducing, if in degree of node becomes 0, push it to the Q and follow the process till Q is empty. So I am doing the same. First step is I calculated the in degree of each vertex, and to the Q I have pushed 0 in degree nodes, and I'm popping out vertex from the Q. Whenever I pop out, I reduce the in degree of its adjacent vertices. And while reducing, if the in degree becomes 0 of any vertex, I'll push those as well. Now I have popped out 4. What are the edges that are outgoing from 4? This is one edge that is going and this is one edge. So when you remove 4 from the graph, these edges also gets removed. When these edges gets removed, the in degree of 1 will be reduced. Here the in degree of 1 is 2, so it will become 1 now. And the in degree of 0 here is 1, now it will become 0. Okay. So while reducing, 0's in degree has reduced to 0. Now I will put 0 to the Q. I will not NQ 1 to the Q because its in degree is still 1. Now that is done. I'll pop out 2. When I pop out 2, I'll add it to my result. So I have popped out 2. When I popped out 2, what will happen? Whatever the edge that is going from 2 also will be removed from the graph. If this is removed, the in degree of 3 will be reduced. It will become 0. Okay. Now I'll add 3 my 2Q. Are there any adjacent vertices or edges from 2? There are nothing. Okay. So what will happen now? I'll pop out 0 from Q. And there are no outgoing edges from 0, right? From this is the 0, there are no outgoing edges. So nothing will be done. I'll just add it to the result. Now I'll pop out 3. When I remove 3, what happens? The edges that are outgoing from 3 also will be removed. Now this will be removed. And the in degree of 1 is 1. This will get reduced by 1. This will become 0. I'll NQ 1 into my Q. Okay. This is done. There are no other outgoing edges. Now I'll pop out 1 from the Q. Okay. When I pop out, are there any outgoing edges from 1? No. And now are there any other edges that needs to be DQ'd from the Q? No. Q has become empty. So my topological sort order is 5, 4, 2, 0, 3, 1. Now let's verify it. What is the edge here? 5, 0. There is an edge from 5 to 0. If you see the topological order definition, for every directed edge in a graph, U comes before V in the ordering. So 5, 0. Here if you see, 5 has come before 0. Okay, 5 is at here and 0 is here. 5 has come before 0. So this is satisfied. And there is another edge 4 to 0. Now here there is an edge 4 to 0. If you see, 4 has come before 0 in the topological order. So this is also satisfied. Now there is an edge from 4 to 1 is an edge. So 4 should come before 1. 4 is here, 1 is here. So this is also satisfied. Now there is let's take this edge 5 to 2. 5 to 2. 5 is the 5 2 is the edge. Okay. Now 5 has come before 2. 5 has come before 2 in the topological order. This condition is also satisfied. Now there is an edge from 2 to 3. 2 has come before 3. This is also satisfied. And there is an edge from 3 to 1. 3 has come before 3. 1. Yeah, this is satisfied. So we have checked for each and every edge in the topological order and everything is satisfied here. So this is not just a single topological order. If you see at the beginning, we have got in degree 0 vertices, 2 in degree 0 vertices, 5, 4. Here we have taken 5, 4. If you would have taken 4, 5, then order would have been different. Let's do that. Let's suppose I have taken 4, 5. So my order will become 4, 5 and 4 force vertices or adjacent vertices are 0 and 1, right? So if I take this order, 4 comma 5 will become first, and now since we pop out 4 from the Q first, what are all the adjacent vertices? 0 and 1 are the adjacent vertices. Now zeros will become like 0, in degree will become 1, and this will become 1. Okay, now nothing has reduced to 0, we will not NQ anything. I'll remove 5 from the Q. When I remove 5 from the Q, this edge will be removed and this edge will be removed. Both will become 0. This will become 0 and this will become 0. Okay, to the Q I will put 0 comma 2. So 0 comma 2 also I can put it in any order. Either I can put 0 comma 2 or I can put 2 comma 0. So 4 5 0 2 and 4 5 2 0 are the two topological sort orders. Now if I go with 0 comma 2, when I remove 0, nothing will happen because there are no outgoing edges. But when I remove 2, 3 will be introduced, like when 3 will come here. Okay, now yeah, here also 3 will come and 1 will come at the end. So these are two more topological ordering that can be possible with this graph. Okay, because since initially we have taken 5 4 in the Q, instead of 5 4 I would have taken 4 5 also. If I have taken 4 5, then you will encounter a case where you have to NQ 0 comma 2 to the Q. Like you can try it out, you can try run it. When I am NQing 0 comma 2, either I can put 0 comma 2 or 2 comma 0. So 3 topological sort orders are possible for this graph: 4 5 0 2 3 1, 4 5 2 0 3 1 and 5 4 2 0 3 1. These are all the topological, these are all the 3 different topological sort orders possible for this. And let's see the time complexity and space complexity. If you see the time complexity, what we have done, we have just done the BFS, which means you have traversed each and every vertex and each and every edge. So it is same as a regular BFS traversal time complexity. So order of V plus E is the time complexity, and space complexity is we are using Q here for Q. So in the Q, at most you can have the number of vertices in the Q. So order of V is the space complexity. Here we are using Q, and one more thing is to store the in degree also. For each node you have to store the in degree, right? For that also you will be needing one more array kind of thing. So order of V plus V, 2V, is nothing but order of 2V. 2V is nothing but order of V. So it is similar, the time complexity and space complexity is similar as BFS method. Yeah, thank you.